In this problem, we're asked to find a Riemann sum approximation of an integral using the trapezoid rule. And we want 4 trapezoids from -1 to 3. So let's just go ahead and mark off the boundary of the integration that we're being asked to find here. So we want to go from -1 to 3. Okay, so this is our A, and this is our B. The first step in any Riemann sum is to find out what the width of a typical area will be. So I'm going to use the formula delta x equals b minus a over n for that. Our b is 3. Our a is -1. And they'd like us to use 4 trapezoids. So this is going to be 4 over 4, which is 1. All right, now we can start to draw the boundaries of where our trapezoids will be. These are the cutoffs between each trapezoid. Now, when we had done a left Riemann sum, we let the left side of the rectangle determine the height of the rectangle. And when we did a right Riemann sum, we let the right side of the rectangle determine the height of the rectangle. This time we're not going to be using rectangles, we'll be using trapezoids. So we're actually going to let both the left and the right determine the height. And what do I mean by that? I mean, for this trapezoid here, the left side will intersect the curve at this point, and the right side would intersect the curve at that point. And what we want to do to create the trapezoid is connect the two. This is supposed to be a better approximation of the area under that segment than a rectangle would provide. So let's go ahead and do it for the others. And we just have to connect the dots with straight segments. Okay, so we've got 4 nice trapezoids here. We want to figure out what the area of each trapezoid is. So a table could really help us to do that. This is going to be trapezoid number 1. This is trapezoid 2 and 3 and 4. So let's list our trapezoids. Number 1, 2, 3, and 4. Okay, now we need an x, a position. An x with which to calculate the height of the function. But for each trapezoid, we need actually more than one x. We need an x on the left and an x on the right. So for the first trapezoid, the position of its left side is at x equals -1. That's this point here. And the right side of it is located on x equals 0. Those are two numbers that are really important to that trapezoid, the left side and the right side. For the second trapezoid, we're going to want to have a 0 for the left side of it, and then x equals 1 is the right side of it. And we'll just keep going like that. For the third trapezoid, we've got it starting at 1 and ending at 2. And finally, the fourth trapezoid starts at 2 and goes to 3. What I want to do next is find the height of the left side, and we'll want the height of the right side. So for this one, the function's a little more complicated than it was in my previous videos. We have a function f of x equals 2 to the x. So the height of that dot on the left is 0.5. The height of the dot on the right ends up being 1. To get that, all we have to do is just do 2 to the negative 1 to get this, and then do 2 to the 0 to get this. For our second trapezoid, its left side has a height of 1, and its right side has a height of 2. For the third trapezoid, the left side has a height of 2, and the right side has a height of 4. And for our last trapezoid, the left side is 4 units tall, whereas the right side is 8 units tall. Now, if you recall from the area of a trapezoid formula in geometry, the formula is base 1 plus base 2 divided by 2, and then multiply that average by the height. But here, let's just adapt it to our purposes and our variables. The area of any given trapezoid here will be f of xl plus f of xr over 2. So just average the two heights of the left and right side, and then multiply by delta x. Delta x is the thickness of the trapezoid. So this is the formula we want to use in our table. You may wish to do it one step at a time. Like, for example, we could get the average height. And for that, we'll just do f of xl plus f of xr over 2. Okay, so the average height is going to be 0.75, 1.5, 3, and 6. We can put in our delta x. And then finally, the area of each trapezoid. Just multiply. Okay, that table looks pretty good. What we'll want to do now is sum up the areas. I get 11.25. And that's the trapezoid approximation. Now we can use a web app to calculate the trapezoid approximations as well. In a search box, type in Desmos trapezoid rule Riemann sum. And you'll just want this one here. It's got an example already plugged in, but we want to use our function, which was 2 to the x. Okay. Let's go from -1 to 3, just like our integral was. And let's let the number of trapezoids be 4. Now I can use the tool, the wrench here, to change the x-axis settings. Like right now it's kind of tough to view. So you can make it appear larger on your screen with that tool. Okay, and this looks pretty much like what I had drawn, so that's good. Now we just have to look at the calculator result, and it tells us 11.25. That matches with what I had thought it was. We can also just see how close it is to the actual area under the curve using Symbolab. So go to Symbolab, and we'll do a definite integral from -1 to 3 of 2 to the x dx. We haven't gone over how to solve that one by hand yet, but we will. But we'll just let Desmos do it here and see what it says. Okay, so the true area is around 10.82. And not surprisingly, the trapezoid rule does overestimate this area because there's a little bit of the trapezoid that is not under the curve. So it's an overestimate.